Alright, it's time again. Let me start with two announcements. Somebody was so nice to inform me during the break of two typos. Those two things. I was saying MD5 all the time, but apparently I left out the D, so it's MD5. If you took notes and it's just saying M5, please put MD5. And the second one, also in the picture, and I was saying it's n-bit strings times n-bit strings, outputting n-bit strings, but I forgot the n in the exponent. So please put an n there. Another request from Gustavo and me: when you submit your homework, put in the subject line WF80. Because Gustavo and I have to figure out how to sort your homeworks, and we're getting lots of emails, not just from you people. And then you can put whatever here, but please put this as a prefix. And I'll put this also on the web page. Sorry for forgetting this on Thursday. Also, there were some questions like, how can you document, how should you document? You can consider us code literate, so if you have some implementation, please send in your implementation. I might not read it, yes?
But what programming languages?
Surprise me?
Haskell? Okay.
I mean, in general, I will not go and debug your code. If your code is wrong, I won't say in line 5 you have something. I will probably not comment on the beauty of your code, but if it runs, it's fine. And I know people like to show off implementing Haskell, but it's not shocking. It's cool, but
no, okay, but okay.
Up to you. I prefer not to receive Excel sheets. So for the first part where I'm asking you to draw, I don't know what your latest skills are. I'm totally fine with a hand-drawn thing scanned. I prefer PDF as format. And then for the code, I really don't care. Don't send me an Excel file. So if you, I mean, it has to be code. It has to be readable code. Don't send me obfuscated C or something, well, whatever. Okay? Were there any more questions that I haven't answered, either in private or here now? Level of documentation. So you asked me at the end of the last lecture. Place me somewhere between math and computer science in what details I want. Don't write me a novel, but give some explanation of what you're doing there. For instance, if you write the order of the matrix is 15, then I expect to get some justification. A justification need not be all 15 powers of C. That is certainly a functioning justification, but it's also kind of laborsome. If you get your computer to print out the 15 powers of C and you just copy them in, that's totally fine. Handwritten 15 powers of C would be kind of cruel and unnecessary. If you send me, here's the one line that I fed through whatever it is that we use for a computer algebra system, and output 15. The thing is, if that line is correct and 15 is the right answer, you're getting 4 points. If that line is incorrect and 15 is not the right answer, it's hard to give partial credits. I mean, give me the whatever you fed through it, and I can at least see what it is. Like, if I don't see what matrix you feed in there, and you just show me like I put in sage.order or something, then I don't know what you put in there. If I see that you're getting 15, you should have gotten 7, but I find that your matrix had the last entry wrong, at least it's like half a point for doing a stupid 0-1 flip rather than apparently this person has no idea what an order means. Okay? Good. In this thing, I was already talking about blocks of messages. So the next topic that we're doing is called block ciphers. And as the name suggests, these encrypt messages in blocks. again have that our message M is some M0, M1, M2, etc. So these here are then the smallest you're going to see 64 and 28 or whatever. It's per block. We will see on Thursday what we can. No, actually, I should see now. What else can do the exercise? Yeah, okay. We'll see now. When you're encrypting such a thing, and you have a message that's longer than one block, one problem is at the end you again need some padding. So you're ending with some bits that are my lowercase letters. So that's like in the previous example, the 384, and then there's some space. So we always need to be padding out until the full block length. So I'm going to pad out the message to full block length. Now, one possibility is you're just doing that CI is the encryption, and I'll now go back to just writing K because now it's an encryption key, and we'll skip authentication for a while of MI. This is called the electronic codebook mode. So this is pretty much as simple as you can imagine. You take your block of message, run the cipher over it, and you're getting the ciphertext. There are some very nice visual visualizations of why this is a bad idea. So first of all, well, codebook means you have a one-to-one translation. If you have the message 12 o'clock alarms, it always translates to the same ciphertext. So if today you see somebody texting now and it's 12 o'clock and it sees 12 o'clock alarms and there is this blob of ciphertext, then if you see in a few days again 12 o'clock alarms, you see the same ciphertext blob, and if you had once a matching plaintext, you'll always have this. So there is a problem with if you ever have a plaintext ciphertext pair, it will be good forever. Also, somebody made a very nice visualization of some super encrypted, super secret encrypted thing. Now you have no idea what this was, right? Can you see it in the back row? Good. So this is a encryption per pixel using ECB. Now probably this was white and not this strange color it is right now. But since you see that all white pixels will translate the same, all previously black pixels are translated the same, you can still see what it was. You also find visualizations of this with pictures of text, and then instead of having black on white, you have pink on green. Maybe not as readable, but you can still see the text. So ECB, because it's locally encrypts, has this problem. So as soon as you have messages that are longer than one block, you can figure out such patterns. So ECB encrypts / decrypts locally, and then, well, if you have that mi is equal to mj, then this leads to ci being the same as cj. So this thing is also called the ECP electronic codebook Penguin. So ECB is not what we want to do. Now remember, these are big blocks, these are at least 64 blocks, so nobody will have a full table of the codebook. This is not weak because somebody would write down 2 to the 128 plaintext ciphertext pairs. 2 to the 128 is still too big. But because we have all these matches, that's what makes it weak. We have all these correlations between things. So what we need to do is we need to chain these better. So we need some chaining to change, well, basing position. So ECB is basically going all the way back to what we did in the very first lecture. Remember that we did all these kind of toy ciphers, all these funny little things where you have like moving around locally, and then from Caesar we went on to Visionaire and we went to Enigma. And then one of the benefits of Enigma is that it doesn't always translate E to F or A to D like in Caesar, but that depending on how the rotors are, it changes the position. So that's now, ECB is back to pre-Enigma crypto. This is really, really bad. So you have a cool cipher, everything is fancy, to the 128 security, and then you use it in that. So don't do that. So one typical case is the cipher feedback. Mode. So what CFB is doing, and I leave my little cheat sheet here also messed up all the little connections. Now that's a downside of little cheat sheets. There we go. So we'll have our blocks of message come in. M0 gets fed into some encryption. So that's where the key comes in. So there's a box here. And then it is output. Now, the output of this thing is then fed back into the next encryption block. Ah, damn it, this sheet does not appear to me. Now, where do I feed it back into? And that's where I always need to check. The encryption only does n-bit to n-bit, so it can't go back in here. I have the possibility to XOR it in here, or I have the possibility to XOR it into here. And so the cipher feedback mode XORs it into the next block. So then the next message block comes in, it gets fed into an encryption box again, and then we output, we branch off, we feed back it into the next one, and so on. And at some point, we're out of messages, so then this is, well, this would be C0, this would be C1, this would be C2. Now, these are little asymmetric, so what we do, similar to how we did it in the string cipher design, is that also here we have an XOR coming in, namely, again, with an initialization vector. So also for block ciphers, if you want to have them in long streams or longer messages, multiple blocks, we do want to have some freshness here. So here we put either a counter or some random string. So we have this thing and then all the cipher texts. chaining up there, and chaining should also be here. So CBC, so then we send the initialization vector, we send all the ciphertext pieces. So this one is sent in clear. Now, when you want to decrypt something, well, let's first write out what the decryption is. So CI is now the encryption under key K, and what we're in there is MI plus the encryption of the previous text. So this is MI XORed with CI minus 1. Now how we get to get the message back? So first of all, we need some form of decryption function. So I mean, what CI is, the last thing we went through is encryption, so we gotta put here a decryption function. To get MI, we definitely need to decrypt CI. And then when we've decrypted CI, we now pass the blocks there, then we still have to undo the XOR with the previous ciphertext. So here we can just XOR with CI minus 1. Now you could cascade this into using something of the message here, but we assume that we have the ciphertext sitting around anyway. So, sorry, this is outside the parentheses. Arc. We're decrypting CI. Once we're done with the decryption, we're XORing with CI minus 1. So when you encrypt, you have to go totally sequential. You can't encrypt block 5 if you haven't encrypted block 4 yet. You need to chain all of those. If you're decrypting, you want to get block 5 decrypted, you can do it quite locally. You need to have the ciphertext at 5 and the ciphertext at 4. So if you're doing a disk encryption, then the encryption, well, okay, you have your big file and you're going forward, and then later on, if you know which part you want to access, you can actually locally go there and just decrypt the part that you need. So that's a nice feature of CBC. That this one gives you here local decryption, but the encryption is sequential. Okay, there's some more modes that I'm going to run through briefly. There's OFB, that's the output feedback mode. So that's yet another of these little drawings, and now it's the upper one, so it's fed in at a different position. I'll draw this nicely. So we have the initialization vector come in again. We have the encryption box. And then OFB is adding the message only down here. And this gives you C1. Now, after the encryption, we also branch and feed it back into here in the same place as the IV was. So this goes into encryption under key K. Then it feeds out. It gets branched off as the next input. It gets XORed with the next message. And these are capital M's. This is M0 getting C0. This is M1 giving C1, etc. Now, this is a quite different design. The message gets never fed through the encryption function. All the encryption function is getting is IV, the encryption of IV, the encryption of the encryption of IV, and so on. So, when I want to write out what CI is, then it's the encryption under key K of IV applied many, many times, namely I plus 1 times. So this means apply I plus 1 times. So for C0 I applied once, for C1 I applied twice, and then I XOR MI to this. So now basically using my block cipher as a stream cipher. Here the encryption is just like in the stream cipher, well, okay, block-wise instead of bit-wise, and then the stream is just a repeated encryption of IV. So here it will be how MI is decrypted, and then OFB uses the block cipher as a stream cipher. What we do is we're encrypting this IV repeatedly. Now how do we get MI back? That's simple as it is in stream ciphers. We just flip the roles. So we need the encryption under key K, I plus 1 times of the IV, XOR CI. So the nice thing is, if we are on a device where we have idle times, we can pre-compute some stream. On the other hand, we need to go forward all the way if you want to go there. So no local access. So we can pre-compute. Multiple encryptions of this IV for some J. But no local access. There are many, many modes. I will write one more, but I'll do that on the top of the blackboard in order to fit there. All of those, you need to do something about authentication. So, very important. Do not forget to authenticate. So all these modes, so block ciphers, in modes, they only encrypt. There are some combined designs which have like a block cipher plus authenticator, a little bit nicer than doing them separately, but most of the times you pick either a block cipher or stream cipher. If you have a block cipher, you pick some mode, and then you make some MAC on it. So typically, we use those as a mix and match. When you pick your preferred block cipher, you pick your preferred stream cipher, and then you have something. Sorry. Your preferred MAC, and then you have something. Last one to show is the counter mode. Counter. As the name suggests, there is some counter. So this one uses an IV like everybody else. It also uses some nonce. So let's call this IV. Just IV. And you have some count. Now what it does is it takes IV, append 0, 0, 0, 0. Then it takes IV, append 0, 0, 0, 1. We counted, yes, IV 0, 0, 0, 0, 1, 0. And then it runs this thing through the encryption function and takes the result, XORs it with the first message block, so that's M0, to get C0. Okay, and then we take the next block, which now has a 1 at the end, we run it through the encryption block. We take the output, we XOR it with the next message block, and we're getting the next ciphertext. Now this one doesn't have any chaining. There's no influence of the first one on the second one, or the third one. But still, if I would do like the ECB penguin, if I have M0 is black and M2 is black, they would be XORed with something else, because here we have an XOR with the encryption of the IV followed by all zeros, and here with the IV followed by, well, 2 at the end. So in formulas, we have that CI is the encryption and the key K of IV followed by, well, this is I in binary. So here it was all zeros for message 0, 0, 0, 1 for message 1. So in general, it's a binary representation, and then XOR the message I. And then, if you read it the other way around, we're getting that MI is the encryption. Same thing is up there. So encryption of IV followed by the binary encoding of I, XOR the ciphertext I. Now this one is fully local. If you want block 15, all you need to do is encrypt IV followed by binary representation of 15. So this is fully local access. Now that part is nice. It depends on how long this counter is. If you have a short counter, say only 4 bits, then this will repeat after 2 to the 4. So after 16 steps, you'll have the same head to add into it. So you need a long counter. So the key stream, and you put key stream in quotation marks because, well, it's blocked. Repeats. after 2 to the b if b is the length of the counter. Now we have our block cipher there. The block cipher can take 128 as input. How much of this do you sacrifice for the counter? How much of this do you sacrifice for the IV? So there's a balance on. The IV dictates how many fresh encryptions you can do. If you repeat the IV, you'll get the same steps after it, because it's a deterministic counter. And the counter determines how long you can use it for. Say if you're using 32 bits for the counter, the longest you can encrypt is 2 to the 32 blocks. So, okay, each of those has, say, 7 bits, so it's getting you somewhere, but it might not be enough for moving encryption. So then you might want to have more in the counter part, say 64 bits, but that means you only have 64 bits for the IV. So you only are allowed to use 2 to the 64 different messages, or 2 to the 64 different communications. Now 2 to the 64 is a pretty large number when it comes to normal communications. But the problem is, are you keeping track of the IV? If it's something you're sure is always increasing, then you're probably fine. If it's something you're randomly picking, then you have to be worried about the birthday paradox. Because if you have 64 bits, then after 2 to the 32, you have a pretty high chance that you're repeating. So you get a trade-off. The number of complications different IDs versus the number, well, versus this 2 to the b. So you could just put in your spec that after 2 to the 32, you're wasting one block and you're sending a new ID. So for example, send IV1, and then you have C0, C1, so C2 to the 32 minus 1, followed by IV2, and then C0, I put bars on it, so I don't have to add to 32 each time. So you can break it down into much, much larger chunks and then waste one package of, well, one block of sending an ID. On Thursday, we'll look at one particular block cipher called DES, which stands for Data Encryption Standard. Now, you might have noticed that the topics I'm covering here are often topics where you can actually break something. So the good news is that DES is no longer the standard. So there is now something which is called AES, which is the Advanced Encryption Standard. The bad news is that your bank is still using DES everywhere. And the really bad news is that it's using it in the weakest form. So this is something which is a 64-bit block. So each of these MIs 64 bits, and it has only 56 bits in the key. So historically, when this came out in the late 70s, even then 56 bits were not considered to be big enough. So at that point, people were like, guys, is this something you want to brute force? Are you just trusting that we, the Americans, have more power than them, the Russians? That was the front lines at that point. Now you would say, well, the Chinese are building all the chips, so they would have the more computation power. So it was something at the edge where the military apparently felt comfortable with civil use of this, because 56 was small enough. In the 90s, late 90s, the EFF sponsored a, was it $250,000 project to build what's called the DES cracker. So that's an FPGA-based design, which is actually cracking DES. And then another 8 years later, so 2006, we had one paper at a conference which was 8,900 something euros to build a nice box with, okay, there was a material cost, it cost uncountable hours of PhD and masters during this time, but that's of course free. You don't count this when you count for it. Like, you do this once and afterwards anybody can build a box for under 9,000 euros, which totally breaks DES. Now, on Thursday, you will not have the box that breaks DES, so we'll just look for more interesting properties. And that's going to be our main example of block Cipher. All right, that's for today. That's it for today.